In this segment, we will look at magnetic circuits, and we need to know about these because we'll need them when we get to a discussion of machines, in motors and generators. So I'll not read through all these bullets, but in this particular segment, we'll look at all these topics. So let's start with a very simple idea that if you have a current flowing through a conductor, it produces magnetic field. So the convention is that if the current, for example, is going into the plane, then it's shown with a with this cross, the end of an arrow, and you can see the flux lines there in the clockwise direction. Whereas if the current is coming at you, for example, from the plane of this paper or screen, then it's indicated by a dot, point of an arrow coming at you, at us, and the flux lines are in the counterclockwise direction. And the Ampere's law says is that if you have a closed path, as shown here by this dotted curve, and this is really a symbol here, it didn't show up, a closed path. So if you take a magnetic field intensity and H and you integrate this over this path here, closed path, then it is equal to the sum of all the currents enclosed. And in this example, you have I1 and I2, for example, going into the plane and I3 coming out. So let's apply this simple idea to a toroid as shown here, where we have a coil of n turns, and it is very carefully shown as it is how it is wound, and you have this current I flowing into it, and we can see that wherever the current is going in here, we can indicate that with a cross here like this. So you have all these n times this current is going in, and therefore these n crosses over here. So if you take a magnetic path at this mean radius r sub m, we assume this toroid is very thin as compared to its radius, and therefore the magnetic field within this toroid, let's assume to be uniform, and we can talk about in in a sort of an approximate way that we want to know what the mean field intensity H is. So let's take this mean radius r sub m, which will be 1/2 times the inner radius plus the outer radius, or in terms of diameters, 1/2 of this expression shown here, and and the mean path length L sub m is just 2 pi times this mean radius here. And if you apply Ampere's law, which was shown earlier as an integral, what it's showing is that in this case, this mean field intensity H sub m in the core would be the Ampere turns that's being enclosed by this dotted path shown over here, this dotted path, and the length is 2 pi times r sub m, mean path length. So that's what we get here. All right. So now we'll look at this concept of flux density. And first of all, the units of flux density, they are Weber per meter squared, quite often called Tesla, here like this. And in air, the field intensity and flux density are related by this permeability mu naught of free space. We think of air as same as free space, and this mu naught in MKS units is equal to 4 pi times 10 to the minus 7 henries per meter. So that's these are the units for permeability here. Now, when we talk about ferromagnetic materials like silicon iron, silicon steel, I should say, then which is used for making these machines, then we have not a linear relationship between the magnetic field intensity and the flux density as we saw in air here, but rather we have this BH loop that we are all familiar with. And of course, we can make a linear approximation by, so these are multi-valued curves, but if we join the tips of all these inner loops, we can come up with this characteristic shown here between B sub m and H sub m. And you know, and if you think of before it saturates, we have a sort of a linear characteristic defining these two quantities over here. So beyond this value here, this begins to saturate here, B sat, and this may be anywhere from 1 to 1.8 Tesla in most common materials that are used. And but before we reach that, we can make this linear approximation here, that this permeability is mu sub m, which is the slope of this characteristic, and we relate that to that of air, which is mu naught over here, and which is the slope of this dotted characteristic here. And in saturation, basically, this characteristic here has a slope similar to that of air. So that's what is the meaning of this statement here. All right. So now let's talk about, we talked about flux density, but what is flux? What is flux and what is flux linkage, and how much MMF do we need to apply in order to get certain flux density or flux in a core? So let's talk about those concepts. First of all, we'll assume that in this toroidal core, the flux density is uniformly distributed. And this flux is flowing through this cross-sectional area, A sub m, of this core, as shown over here. So you can see that if flux density is uniform, then the flux lines which are crossing, they can be represented by this flux phi sub m, which is the flux density times the cross-sectional area, where the flux density itself is equal to mu sub m times this magnetic field intensity. And this magnetic field intensity is from Ampere's law, we saw is equal to Ampere turns applied to this core divided by the mean path length L sub m, which is this mean path length L sub m over here, right? So now what we can do is we can substitute H sub m from this expression into here, and then we can substitute B sub m from here to here. So it gives us that this flux that we have in this core is given by this expression, which we can rewrite with the Ampere turns in the numerator, and the denominator becomes this quantity over here, mean path length divided by the permeability of the core and the cross-sectional area of the core, and this quantity here we'll call as reluctance. So just restating these things here, we have this reluctance here given by this expression here. So it says, if you want to make an electrical analogy, you apply a certain voltage, and the voltage would be analogous to this Ampere turns, quite often referred as by the symbol F, and this is also Ampere turns we'll call MMF that we are applying. So that's sort of equivalent to voltage in electrical analogy, and this reluctance is equivalent to resistance, and that results in current, which is equivalent to this flux over here. So if you want to make that electrical analogy, you can, but it's really not necessary. The other thing is that when you this flux phi sub m is linking all n turns, so we define another quantity called flux linkage, which is lambda sub m. And as I mentioned to you earlier, the MMF is defined by this quantity F, which is the same thing as the Ampere turns acting on this core. Yeah. All right. So now let's make it a little more interesting here by introducing an air gap into this core. Because when we talk about machines, which we will later on in this course, we always have an air gap, because we have a stator which is stationary, and then we have a rotor which is rotating. So in fact, we have two air gaps for the through which the flux lines have to flow. So with this air gap cut into this core and of this length L sub g, which is usually, we'll keep it very small, but nevertheless it's there. And so let's apply Ampere's law and again talk about mean path length here in the core itself. This mean path length here is L sub m here. So you can see that applying Ampere's law, you have the magnetic field intensity in the core, which multiplied by this mean path length, plus the magnetic field intensity in the air gap times the air gap length L sub g should be equal to n sub I, the Ampere turns that we are applying, right? And B sub m and H sub m are related by the permeability of the core, and B sub g, the flux density in the air gap, and H sub g are related by mu naught over here. So what we will do is we'll substitute for H sub m and H sub g from here in here, and we'll get this expression here. And if you recognize that the flux lines which are forming a closed path here, we are ignoring any leakage here, that this flux is equal to the flux density in the core times the cross-sectional area in the core through which these flux lines are flowing, times, and this is the same as the flux density in the air gap times the area of the air gap. Well, the area of the air gap may be slightly larger than that in the magnetic core because the fringing of these flux, and that we can take into account by increasing the width of this core by the air gap path length, and similarly the depth of this core, increasing it by L sub g over here. But for our purposes, we can ignore this fringing, and then this area here would be equal to this area here. But nevertheless, we have an expression for flux densities in terms of flux, and we'll substitute B sub m over here and B sub g over here, and that will give us this expression here for flux. And you can, by properly arranging these terms, you can see that what we have is this term here, which is the reluctance for the flux lines in the core, and this term here gives us the reluctance in the air gap. So this R sub m, not R sub m, reluctance I should say, reluctance of the magnetic path, reluctance of the air gap, they add up to give us the total reluctance in this core, and the flux that we get is the MMF acting F divided by this reluctance here. So we can take into account the air gap, and quite often the reluctance offered by the magnetic path here is much smaller, not zero, but much smaller, let's say negligible, and so this overall reluctance is more or less equal to the reluctance offered by the air gap here. Okay, now next thing we'll look at is the concept of inductance. Usually we think of inductance L as just voltage and rate of change of current, L di dt is equal to voltage, but this L is really a magnetic structure with coil around it as shown over here. So let's say that you have again a toroid, and it has a coil with n turns, and this then has an inductance L. So let's see how that comes about. Well, first of all, we should recognize that the inductance that we define is really the flux linkage of this coil divided by the current here. Okay, so let's say that we introduce some current into this coil, and this will produce a magnetic field intensity, H sub m, in this core, which is the current times this term over here. Well, this magnetic field intensity would produce a flux density in this core, which is H sub m divided by, is multiplied by mu sub m. Then this flux density flowing through a cross-sectional area of the core would give us this flux, and this flux linking end turns would give us this flux linkage. And like I mentioned earlier, this inductance is really the flux linkage divided by the current, and that you can see by multiplying this term, this term, this term, and this term, this term, and this term over here. All these, this term, this term, this term, and this term, they all multiplied would give us n squared in the numerator, and in the denominator we'll get this here, which is really the reluctance of this core over here. Okay, so that is what is shown here, that this inductance is n squared divided by the reluctance here. So under linear conditions where the magnetic structure is not saturating, the inductance does not depend upon the current, just like the resistance it does not depend upon the current. Similarly, the inductance is a property here, which is independent of the current that is flowing. And of course, the energy stored in this magnetic circuit can be, we know it's half Li squared, but it could also be expressed in terms of its magnetic quantities as this energy density times the volume of this core right here. So that's what is written, that this energy density is equal to this value. So that can be shown very easily by substituting for the current in terms of magnetic quantities, and similarly for the inductance to come up with this expression here. Okay, now we'll shift gears and we'll look at Faraday's law. And what Faraday's law tells us is that when you have a change of flux linkage, when you have d lambda dt in a coil, there will be an induced voltage. Okay, so let's say we have this coil made up of n turns, and all these n turns are being linked by this flux phi. Then lambda is n times phi, so we can also express this in terms of n d phi dt as shown here. So we know this from our previous courses, but what we generally don't see is how it is n d phi dt, why not minus n d phi dt? It can be. It depends upon how we define the voltage and the flux direction here. So one easy way to do this is, let's say you have this coil of n turns, and we arbitrarily select this polarity, let's say, plus here and minus here for the induced voltage, right? And now we have to recognize that this flux need not be produced by the current shown here. It could be produced by another coil which may be at the bottom over here and linking this coil over here, right? So, and it's totally possible. This coil may be totally open circuited, but if you have a change of flux or flux linkage, then there'll be an induced voltage here. So what we will do is we will, using the passive sign convention, we'll say that a current is going into the positive terminal with the direction shown over here. And if this coil is shown with how it's wound very clearly, then you can see that this current is going in here and coming out here, and the flux would be in this direction shown over here. Okay, and once we have obtained the direction of this flux, we can forget about this current here as if it never existed. All right, so now we can very clearly say that this induced voltage here is N dphi dt, where flux is defined in this direction here. So that's one way to do it. The other is so-called Lenz's law, and we will not get into that. But this Lenz's law also would help us define the polarity of induced voltage for a given flux direction and how that flux is changing. But nevertheless, we have to pay attention to defining the voltage polarity and the flux direction. And please note that this equation has nothing to do. It doesn't include this current I. Let me delete all this ink here. This expression here does not include this current over here. Okay. All right. So continuing this discussion of Faraday's law, that if we have a current varying sinusoidally, as shown here, this flux here would also be varying sinusoidally, as shown here. And so flux and current, they are plotted to different scales. And by Faraday's law, the induced voltage would be plotted over here and shown with this polarity over here, like this here. So you can see that if flux is varying sinusoidally, this voltage would be varying cosinusoidally over here. Okay, and and we can also relate the flux, voltage, and current, because L, as we know, is flux linkage divided by current, and flux linkage is N phi over here. I, as we know, is from just looking at this expression, this current can be written as N divided by L times phi, and E is N d phi dt. So you can see that this voltage can be related to the rate of change of current by this inductance. And this is the equation that we know already. The other thing we should understand is leakage inductance in magnetic circuits. When we have electrical circuits, especially under DC conditions, we don't worry about leakage currents. But in magnetic circuits, because the relative permeability between the air or free space and the magnetic material is not too different like it is in copper and air for electrical currents, we will have leakage. And so you can see here that you have, let's say in this magnetic structure, you have this coil of N turns, and our intent is to produce flux through the air gap over here. Okay, so you can see that this magnetic core is like a conduit of flux lines. So we'll hope that all these flux lines would remain in this conduit, but that's not going to happen. In a magnetic structure, you will have so-called leakage flux through the window, and what I'm showing here is this leakage flux linking all N turns, but in practice, some would link only partial number of turns. But we'll simplify our analysis by saying that let's think of this consisting of two fluxes. One is this magnetic flux, which is entirely in the core and crosses this air gap as shown here and links all N turns. And then we have a leakage flux, which is flowing through the window of this core, but also links N turns over here. So we can see that this total flux that we have is the sum of the magnetic flux and the leakage flux here. So if we go to calculate the flux linkage, N times phi, we'll have the flux linkage due to the magnetic flux and the flux linkage due to the leakage flux over here. So now let's divide this equation here, both sides of it, by current, and we get this here. And we know that the flux linkage divided by the current is the self-inductance of this core. And this self-inductance would consist of this term, which is the magnetizing inductance of this core, and this term here, which is the leakage inductance here. Okay, so we can see that this self-inductance here is really the sum of these two here, and then if we multiply both sides of this by I, we have this expression, and if you take the derivative of that that gives us the total voltage, which is the sum of this term here. Let's call it E sub m, which is shown here, and then this term over here, which is the leakage voltage across the leakage inductance, shown over here. Okay, so you can see that even though the flux lines are in parallel, the voltage due to these two, they are in series, making up the total voltage. So we get this circuit here, and so what we will do is we will understand this equivalent circuit by saying that, let's say that we take the effect of the leakage out explicitly. So we have this core where there is no leakage flux. So here there is no leakage in this core leakage, okay, because we have taken its effect out explicitly, and so this E sub m is shown here, being produced by the rate of change of phi sub m over here, and then we put the effect of the leakage flux due to this by means of this leakage inductance shown here, and the voltage drop E sub L over here. And then we can also put the resistance of this coil to make the circuit complete. So this is a very useful circuit, as we'll see when we go to discuss transformers. So that brings us to the end of this segment, where we have seen Ampere's law, Ampere turns, how these Ampere turns are needed to create magnetic field intensity and flux density, or flux in the core. We learned the concept of reluctance, and this inductance L is just n squared over the reluctance. And then we saw Faraday's law, E is equal to n d phi dt, and we also saw this fact that in magnetic structures, we have to deal with leakage fluxes, which can be represented by leakage inductances.